So we'll move on to our next speaker. We have Leo Jose, who's an FAE from SanDisk, India, right? Very experienced senior FAE at SanDisk, with a demonstrated history of working in the semiconductor industry and a very strong engineering professional, skilled in embedded software and hardware. Come on, Leo.
Thank you very much. I feel really humbled being over here among really highly experienced people. Definitely I'll get to learn a lot myself. So my name is Leo, I'm from SanDisk, and okay, sorry about that. So I'm from SanDisk, and now we are part of Western Digital. So Western Digital is now a combination of three large companies: WD, SanDisk, HGST. So what this has done is it has brought together companies making diverse storage devices into one large unit. So we are kind of the largest storage company in the world right now. But more importantly, what it has done is it has enabled us to make storage devices that span an entire spectrum. So from really tiny micro SD cards, eMMC devices, to client enterprise grade SSDs, to JBODs, JBOFs, and finally archival solutions that run into petabytes of storage. So anything that you want in an IoT solution, from say edge storage all the way up to cloud storage, is something that we have in our portfolio. Now, we talk a lot about data, but we need to know how to efficiently store data if we really want to use it. And the data needs to be reliable, because if data is lost, there's really no meaning about it. So storage is also a very important part of any kind of application, especially IoT. So my presentation will talk about two aspects. One is about data on the edge, okay, and how it is growing. And the second part will talk about flash storage and how it efficiently handles data that you want to store on the edge. So an analysis tells us that by 2020, there'll be around 30 to 50 billion devices connected, IoT devices. That's huge. And the amount of data it will be generating is around the tune of 115 yottabytes. So 1 yottabyte is like a million exabytes. But not all the data will be stored. Okay, the amount of data that will be stored will be a small fraction. It will be around 1,600 exabytes, which is 0.0001%. And this data would be analyzed on the edge, on the storage. Although a small fraction, it's still a sizable amount. So you can understand the amount of storage needs that's going to grow in the market. And out of the data that is stored on the edge, a very small portion, only 4%, will get stored onto the cloud, mainly for data analytics, offline analytics, data management. So you can see there's a big discrepancy between the storage requirements on the edge and storage requirements on the cloud. Now, the current infrastructure is kind of not built efficiently to handle IoT kind of data. The reason is because the amount of devices are increasing at a very rapid pace. So which means the data requirement will also increase at a very rapid pace. And if you try to rely on a cloud-like system to handle all this data, there will be all kinds of problems. So the optimal solution here is to perform local compute on that data. So you get data, you perform computation on the device itself. Other option is to use peer-to-peer network communication. So you have multiple devices on a network. They can share data and share information about the device. And so edge compute is what we are looking forward to. Now, traditionally, what you see as scenario one is what we were looking as an option to store and compute data. So you have a sensor that transmits all the information onto the cloud, raw data, or could be compressed data also. And then you do all the analysis. But the problems is that you cannot get real-time analytics when you do this. There are a lot of latency constraints. The amount of bandwidth you will need and the cost implications, they're huge. So then we look at other two scenarios. So the second scenario talks about a sensor, and then you have an onboard compute and storage. So all the processing happens on the board, and only a limited amount of data is stored onto the cloud, which you can use for later retrieval and analytics. There's a third scenario where you have multiple sensors that connect to an edge gateway. So the connectivity could be something like, say, a Zigbee network or home automation that we talk about. All the analysis happens on the gateway, and then a small portion of that data goes onto the cloud. We can also look at situations where you have scenario, the second and the third scenario combined together. So any kind of combination is possible. Also, there are some other interesting studies, as you can see. So these are excerpts from Huawei and Nokia. So the one on the top right is a graph where you have placed IoT kind of applications across two axes. One shows the latency, one shows the bandwidth. So as you can notice that all the applications that require very low amount of latency, that's 10 millisecond or lower, fits into a solution where you will need to do edge computing because you need to have quicker data access. The ones higher can do with edge, with cloud kind of storage. And also the amount of bandwidth that you will require for each kind of application. On the left is what we call a 5G hypercube, where Huawei is looking at how to use 5G network for communication among different devices. So again, you have the bandwidth, you have the latency, but on the y-axis or the z-axis, you have the number of links. So we're talking about a mesh network with devices communicating to each other over a 5G network. So again, there'll be local compute that happens on the device and data will be shared among each other. In April of this year, when the CEO of Microsoft was talking about cloud computing and the roadmap ahead, he did mention that edge is a very interesting concept. Whether it's IoT kind of application, automotive, retail, computing is slowly coming towards the edge. So basically the data that you capture needs to be worked upon. So even though Microsoft is looking at cloud as their main roadmap, but they still acknowledge the presence of edge and edge computing. So now how does flash come into the picture in all of this? So in the middle we have the function. So when you have a flash storage on the device, basically it does the primary functions of storing your OS, your application, your boot code and all that. You can create a database also on the device. You can do video analytics on the device. Now what it enables is when you have a really fast storage, you are able to write and read from the storage at a tremendous pace. Okay, data is available just at the moment. So you can enable things like video analytics, machine-to-machine communication. And what it helps you to overcome is the large bandwidth access on the cloud, the excess cost, the latency that you have to go through when you use a cloud kind of a system. Now there are two aspects when you use a local storage. Like I mentioned, one is you're storing OS, boot code and application code. Now you normally write this only once during the lifetime of the device, or you might upgrade it very infrequently, but you're going to read a lot from the device. So that requires the flash storage to have a very high amount of data retention or reliability of data. It's a very important aspect. The second thing is you're storing data. So where you're going to do a lot of writes into the device, less reads but more writes, where the endurance is a very important factor. Now these two actually go hand in hand. If you're doing a lot of writes or a lot of reads, it actually does affect the flash. So when you invest in a flash device, it's always good to go through the data sheets or the specs to know what is the retention, what is the endurance. Usually the retention would be in the terms of how many years at how many temperature, or at what temperature it can survive. It could be say 10 years, it could be 8 years. Endurance would be how many times you can write to the device in terms of write erase cycles or terabytes written. So when you purchase flash, like say as a regular customer, we go to the store, we buy a SD card, a micro SD card. What is that we look for? We look for, one is yes, the cost. Okay, if it is cheap, okay, I just need to store data, it's good enough. Or I could look for performance. If it says it has got really high speed performance, or it is using say it says extreme on it or pro or something, yes, it gives you the best performance on it. But when you design a product, you need to look beyond that. There are a lot of other parameters also that go into choosing a flash device. One is of course the read-write performance measured in megabytes per second. The other thing is the endurance, which I just talked about. So the picture on the right is kind of an analogy. Okay, you write on a paper, you erase it. You write, you erase. Eventually, what happens? Eventually, you'll start ripping the paper apart. Flash behaves somewhat similar. Each time you write into it, you're actually generating a lot of voltage inside the flash. It does degrade the flash at the cell level. So there is a limited amount of endurance that every flash can give you. And obviously, we test our devices. We have the kind of firmware that manages the flash and tells you that this is the amount of write erase cycles that you can see during the lifetime of the device. Data retention. So once you write data into a device, okay, let's say we have a USB device, we write data, put it in our drawer, and we hope, in the next 10-15 years, we'll be able to retrieve data from it. Well, you may be mistaken, because flash cells are affected by temperature. And if it is left unpowered for a long amount of time, you may actually lose data, just like leakage of electrons. So data retention is also very important. And there has to be good kind of firmware running underneath to ensure that data is reliable each time you read from it. Reliability. You see, flash by nature is really bad. So you need to have a good amount of error correction running in it. So the kind of ECC algorithm that runs on it ensures how reliable the data is each time you read it. When you start using the flash initially, it will always work perfectly. It's only after, say, a year, 2 years, 3 years down the line when you actually see problems cropping up. That is when these ECC checks really help. The temperature range. So not all flash devices work across all temperature range. So they have to be tested across the temperature range also. So that's also one parameter you need to look at. Security. Again, security is a very important factor. So data can be stored in the device, but how do you ensure its security? You could use encryption, software encryption, hardware encryption. Also, you could lock your device, which means you can only access the device if there is a software password given to access the device. That's also very important to look at. Also, there could be other special features involved when you use a device, because apart from being just dumb storage, you want to do something more, something that can aid in your application, like say host lock, a password lock mechanism. So on our SD cards, we have the small switch. That's basically a hardware lock. Instead, you have a software-based password locking mechanism, which is again useful. Health monitor. So now you know that flash degrades over time. So it's good for you to know what's the life of the flash that's remaining, because you don't want field returns. At least your host will know, okay, this much flash, this much health is left, so let's take some action before it dies. Last of all, price and availability. So the technological innovation that we do on a year-on-year basis, okay, we are working on different flash technology. Okay, we are going from 19 nanometer to 15 nanometer and smaller. We are going from 2D NAND to 3D NAND. The reason we do that is so that we can get denser flash into a small die, and thereby we can reduce the cost of flash. So that's the aim, to reduce the per gigabyte cost of flash year on year. These are some features that we have embedded into our devices. These are very vendor specific, and we have all kinds of APIs and application notes available for you to access them. Health status. Why it's important is, let's say today you deploy your device, assuming the kind of workload that it would be available to the storage. Say a year down the line, the workload increases, something you didn't expect. Well, the health of your flash is going to degrade faster. So it's good to monitor the health and then take some corrective action. Power immunity. Any kind of IoT application running on battery or power could have a lot of fluctuations on the supply line. So there is an inbuilt power monitoring device which looks at the power and ensures data integrity. So apart from storing data, the integrity of data is also important. So if the power is not reliable, it will go into various power modes, disabling the writes, sending write aborts to the host, and thereby the host can then take some corrective action when it regains its regular power supply. Read refresh. So remember the retention I talked about. So when data is written once, not and just read more often, it might tend to dissipate or go. So when it's powered on, there's an internal refresh mechanism that just keeps reading from the blocks and moves blocks around if it finds that a certain block is going bad. So let's move it to a good block. So that's read refresh. Programmable string. So how about you plug your card inside and then you're able to read out a unique register which calls out the name of your device, of your company. So you know when you get a card, okay, this belongs to you. Host lock, it's a password lock mechanism. And secured FFU. So basically you want to do over-the-air upgrade of the firmware of the flash device. You need to have a secure way of doing it, which is again inbuilt in the device. And finally, this is the entire portfolio of devices that we have. On the embedded side, eMMC, micro SD, SD cards, as well as thumb-size USB drives. We have a stall outside. My colleagues Jesse and Shyam, they'll be really happy to answer your questions. So do visit us, and we can take all your questions there also. That's it. Thank you very much.
Hey, thanks, Leo. Thanks for the wonderful presentation. So, can I have Rajiv Kushu to give away a memento to Leo? Rajiv Kushu is also on the board of IESA, and Rajiv is a director at TI.